Okay. Welcome again. So, for the people who are joining us right now, we will be the hosts of today's session. I'm showing you. Right. And today we're going to talk about, so our speaker for this session is going to be Sania from the Maths Department in Tiago. So Sania did her master's in Pune University. She's originally from Satara in Maharashtra, and her interests are in
representation theory. So I work in mathematics, which has to do with symmetries and studying them using matrices.
Right, great. So over to you, Sania.
Thank you. So good afternoon, everyone. I'm Sania Wag, as I said. So today I'll be talking about mathematics and cryptography. So let me begin by saying, have you seen these two images before? Yeah. So if you have seen this, you know that the first thing you see when you are doing some online transactions like buying things, and the second thing is seen in your WhatsApp. So what is the first thing saying? It's saying that there's something called SSL, which helps you protect your passwords and PIN when they're communicated from your computer to the server. The second thing tells you that no one, even WhatsApp, reads your messages when you send them to your friends. So how do these systems work? We'll see this today. So they use something called cryptography. So what is cryptography? Cryptography is the science of hiding the meaning or content of the communication. So as we saw before, it is used for communicating over the internet, keeping your pins and passwords safe during online transactions, and these days in digital currencies. So people always had secrets. So let's see historically, the earliest known use of cryptography was in Egypt in 1900 BCE. After that, this is very popular, this Caesar cipher. It was used by Julius Caesar, a Roman general, around 100 BC to 45 BC. The third thing, so Julius Caesar, they used things like this to encipher their messages. So the third thing is an Iraqi mathematician called Al-Kindi. He wrote a book about cryptography. So this is one of the pages of his book. So if you have seen the movie Imitation Game, you'll be familiar with this, the Enigma machine, which was used in World War II by the German army for encrypting the messages. So a lot of Polish mathematicians had started breaking the Enigma before Alan Turing, and he used a lot of logic and broke the Enigma along with the people at Bletchley Park, and it shortened the war by a considerable amount of time. So we'll now discuss what is our setup here. So say you and your friend are sending each other messages, and you don't want your enemy to read them. So what you do is you decide on a method to jumble up your messages. So this is called a cipher or an encryption system. And you use a key, that is a password, to jumble up, encrypt, or unjumble up, decrypt the messages. So this is our setup. We'll now see some methods, that is cipher or encryption systems. The simplest one is the Caesar cipher, as was mentioned. So you start with a key 3. So our key here is 3. What you do is you have the alphabets. So you replace the alphabet A with, you shift the alphabet A with the third position after A. So A will go to D, B will go to E, and so on. You have all the alphabets. So you replace, in your message, you replace A with D, and so on. So this way you can encrypt your message. So can you break this cipher? That's the question. If you can break this, it's not very useful, is it? So the cipher can be easily broken. So for a long enough message, you can do that. Let's see how you do that. So we have this information that E is the most used alphabet in the English language. So in the message, you count the number of times each letter occurs. And the one that occurs most is most probably E. So once you know what E corresponds to, you can decode the entire thing without knowing the key. So this cipher can be easily broken. So we need more complicated ciphers. So one such example is the polyalphabetic ciphers. So the Enigma machine that we saw is a uses this polyalphabetic cipher. So in the Caesar cipher, we saw that one alphabet gave you one input alphabet, gave you one output alphabet, that is A was replaced with B. But here, for more complicated method of encrypting, we'll use multiple alphabets to encrypt. So let us see an example. An example is a Wegener square. So this huge square is called the Wegener square. So the method works as follows. You fix a keyword. So before we had fixed a key number, now we'll fix a keyword. So our keyword here is say window. And so you are transporting this message to your friend that this is a secret. So what you do is you write your message here. You write your keyword below the message. So you have these pairs of letters now. So you look at these two letters, T and W. You look at T in the row, T, and W in the column, and you pick up the corresponding intersection, P. So your encrypted text will be P. So this way you can encode all of the messages. If you see in both the methods that we saw until now, the Wegener square and the scissor cipher, the key was an important part. You required the key. Let's say if you and your friend lived far apart, and you had to also communicate key to them somehow, and your enemy found the key in the part of communicating, what would you do? That would be really problematic. So we'll move on to new method of encrypting, which avoids this problem. So this is called the public key cryptography. So as I said, until 1976, this following method was used for encryption. So you decide on a method to encrypt. This method can be public. So your enemy can know that you are using a scissor cipher or the Wegener square. You decide on the key. This cannot be public. If this were public, your enemy will know what you're talking, what your messages are. And then you use this key to encipher and decipher the messages. So this was followed until 1976. But as we saw that communicating the key to your friend is risky. So what if, this is the question now, what if there was a system where communicating the key is not required? So all the information is public, but you can still communicate secretly. So this, we'll look at an example of such system. It is called the RSA encryption system. It is part of public key cryptography thing. So very roughly, this method is the following. So you have a lock which locks without a key. You send your friend a box with this lock. The lock is open, it's not locked. Yes, only you have the key to the lock. You keep the key to yourself. Now your friend locks the message in the box and sends the box back to you. Since you have the key, you can open it and get the message out. So roughly this is how it works. So we'll see now how mathematics is used in this system. So as before, locking the box was easy. So you could just lock it. Both you and your friend could do it, but unlocking the box is hard. So we want some process that going forward is easy, but reversing the process is hard. So this is where math comes to rescue. So it is easier to multiply two large prime numbers, but it's much harder to factorize them. So the bigger the size of numbers, longer it takes. So just to give you an estimate, so if you had a 200-digit prime number, it would take this many years. If you had a 200-digit number, sorry, not prime number, a number, it would take this many years to factorize the prime number. So this is a large amount of years. We'll look at one other method, which is part of public key cryptography. It is called the Diffie-Hellman key exchange. So this method is used to create a shared key. So before we were just transporting messages to one another, now we'll create a shared key using the public information. So this system was given by Diffie and Hellman in 1976. So the story behind this is that when they first tried to publish this method, it was considered to be so important that the government thought other countries could use it during war. So they stopped the scientists from publishing this method. And we shall see what this method is. So let me warn you, now we'll look at some math that will be used in this method. So counting on clocks. Say you ask your friend to meet you 4 hours after 9 a.m. So what time do you meet your friend? So it's either, 1 o'clock. So you can say it's 1300 or 1 p.m., right? 1300 is the military time. So both of these times are same. So this inspires some new kind of addition, which is called the modular addition. So what you do is add the numbers as usual. So you have 9 and 4, you add them as usual, that's 13. And then you compute the remainder after dividing by 12. That is your 1 p.m., the answer, the new answer. So this is called the modular addition, which is an addition on this set. The numbers are 1 to 12. We'll look at some examples. Say you had 5 and 8, so you add them as usual, and then you compute the remainder after dividing by 12. So this is like 5 p.m. and 8 hours after 5 p.m. is 1 again, and so on. So you have 6 and 9, that is usual addition is 15, but you divide by 12, the remainder is 3. The third thing is interesting. So if you have 2 p.m. and then 10 hours after 2 p.m. is 12 p.m., which is 0 again. So you have something like the 0 in this addition, in this modular addition. So we'll make some observations about it. For any number a, if you add 12 to it, modulo 12, you get back a. So this 12 behaves like a 0. So in the usual addition, if you add anything with 0, it gives you back the same number. For any number a, you have, if you add 12 minus a to that number, you'll get back a again. Sorry, this should be 12. You'll get back 12 again. So this behaves like a negative of a number. So if you lived on a planet that had only 5 hours, you'll do something like addition modulo 5. This is, you'll add the numbers like usual and then compute the remainder modulo 5. So like 3 plus 4 would be 7, and then it will be 2 modulo 5. 2 plus 3 is 5, which is 0. And 1 plus 2 is 3, which remains 3 after dividing by 5. So similar to modular addition, there's something called modular multiplication, which is you define it for on the set 1, 2 up to p minus 1 for a prime number p. So you multiply the numbers as usual, you divide by p, and the remainder is the answer for the new multiplication. So why do we consider primes here? Because this set then has an 0 and an inverse, something that acts like a 0 and something that acts like an inverse. We'll see some examples of modular multiplication. So say, again, I had p was 5. So if I multiply 3 and 4, it's 12. So I divided by 5 and the remainder is 2. Similarly, I have 2 times 3 is 6. And if I divide by 5, the remainder is 1. And I have another example, like 1 times 2 is 2. It's again 2. So why did we do all of this? To explain the Diffie-Hellman key exchange method. So I'll explain the method now. So all of these computations are here modular prime, which we saw just before. So what you do is you fix a number g. This is a special number, g is fixed, and this can be known to everyone. You start with your own private key. So you have a number in your mind. This is not shared with anyone. You don't have to share it with anyone, not even your friend. Your friend similarly has a number b in his mind. He doesn't share it with you. So you compute g power a and send it to your friend. Your friend computes g power b and they send it to you. So now both of you have this number, g power ab. You have it as you had g power b, which your friend had sent you, and you can compute this number, g power b power a, and your friend has it because you had given them g power a and they had b. So they can compute this. So now both of you have this g power ab, the number g power ab. So your secret key is g power ab. So now the question is, if your enemy can know the communication between both of you, they'll have the knowledge of g power a, g power b, and g. Can they find the secret key g power ab? So it's very difficult. So the longer the prime, the longer it takes. For example, if you have a 240-digit prime, it takes approximately 3,100 crore years for the enemy to figure out the key g power ab. So we can make the system even more complicated using mathematics. So we used a new multiplication based on clocks to do our multiplication. The multiplication had these properties. It had something close to 0, something which acted like a 0. It had an inverse. So we can consider objects with some multiplication that have this property, and such objects are called groups. So then the question comes, can you use other groups in cryptography? So the answer is yes. Elliptic curves are kind of groups that are an example that are used today in cryptography. So elliptic curves are actually curves, and you define the addition on them geometrically. So these groups are of interest to mathematicians. They're recently used in proving the well-known Fermat's theorem, which you might know, as this is a statement. So this is something for you to try out at home. And that is all. Thank you. Yeah, thank you. Thank you. No, not there. Sit on. Okay. Sorry. Thank you, Sanya. That was wonderful math talk mates portrayed in such a simple manner. We will open the floor for questions. We have a lot of time. Can you talk? Thank you.
SHA. Standard hashing algorithm.
No, I'm not familiar with it.
Okay, fine. Because it is a part of cryptography, right?
I see. Yes. I am actually, I do mathematics. I'm the mathematics side. I'm not familiar with computer science.
I have a question.
Yeah.
So in the RSC system that
Right.
show, so how is that box being sent? So I understood the rough idea, but how is that worked out mathematically? So how do you do that? So you are sending a box that is unlocked to your friend.
Right.
With and you have, and then he can put whatever message he wants in the box.
Yes.
Close it. Anyone can close it.
Right.
And he sends it back.
Yep.
You are the only one who.
Yes.
So now the question is, how is this done mathematically? How is it like in the DPLS, you shown this mathematically to generate a G for the FP cross field and then to work out the G bar A.
Yes.
How does it work?
Okay, so in RSA, you take a composite number n, which has two prime factors p and q. Only you know the prime factors p and q. You send the message to you have some public number like g, which was fixed during Diffie-Hellman. That kind of number you have, and so you're. I can actually explain it to you later. It will take some time. Yeah. We have a question somewhere over here. Okay, this is coming from a biologist. Right. When we talk about encryption, say for WhatsApp, we normally get these encryption thing. Can you tell us about that exactly? How is that encryption happening? That in very advanced terms for someone like me to understand that. Yes. So what WhatsApp? So you have texts. First, WhatsApp does is converts text into numbers, and then it so you have like a big chain of numbers now, and it does some operation on this big chain of numbers and jumbles it up. But the operation is known, and it sends the jumbled up number to the other party, and then the other party gets back unjumbles the number and gets back the message. So this process of jumbling and unjumbling should not be known to all the people. Like everyone should not be able to do this. Otherwise, they can intercept the jumbled message in the middle and get your message back. So that is where cryptography comes in. Like the process of jumbling and unjumbling. We have a question there. I have a follow-up question to that. Yes.
Maybe you can wait for the mic.
I have a follow-up question to what you just asked. How do you ensure that the jumbling and unjumbling does not get public or does not get known? How does that part?
Yes, so we looked at public key cryptography. So there were some elements of jumbling and unjumbling that were public. So where is it? Yes. So here. So as in the Diffie-Hellman case, some parts, so this G, number G was public, it was known. Even your method can be known to everyone, what method you are using. But to actually unjumble, so that you have this number back, to actually unjumble, that is from the known public information to get back the key, it is very computationally difficult. That's the method. It's computationally difficult. It takes like long amount of time to unjumble it. That's how it's done.
Thank you.
We have one more question here.
So I don't know clearly, but I've heard that blockchain works on encryption. Is that true?
Sorry, what?
Blockchain.
Blockchain. Oh, there's something called blockchain. Yes, I'm very familiar with, yes.
Like, can you, like, if you know little, you should probably know more than me. So
No, I do mathematics. I'm not really a computer science. Do you know anything about it?
So your question was whether the blockchain uses encryption or not?
yeah,
Yes, it absolutely does. Blockchain as a model cannot sustain itself without encryption because it's about putting everything in public so that, see, usually what is blockchain used for? It's used for a lot. Well, I'm not very much aware of it, but the idea is that you are doing transactions, but then whenever you're doing transactions, usually you initiate a transaction and everything is taken care of within the bank. You have no ability from side of the inside that you cannot inspect each and every process that is happening inside the bank for dealing with your transaction. You can see something about it, but not each and every process. Blockchain also takes all of that and puts it as is, and puts it in a public forum, so that whoever has the authority to inspect can inspect. But it's all good. The information is all there, and it is protected from other people by encryption. So you need encryption to make any of this. Because this is a very naive introduction to blockchain because it might be actually wrong in some places. It's what I understand as a complete layman as well. And that's the thing. Encryption is central to a protocol like blockchain. Okay. Like if you have a follow-up question, we have time. Like it's okay. You have something else to ask? Okay, fine. There's a question in the front.
Are there any other encryption systems that are currently in use apart from the Diffie-Hellman key exchange method?
Yes, this, so the end said this Diffie-Hellman key exchange on elliptic curves. Even Diffie-Hellman was used until recently, but now since we have faster computers, it can be somehow broken. But these Diffie-Hellman on elliptic curves is used recently. There are other variants of these as well. Yeah. I think there is another question, follow-up question over here.
Yeah, we can take that.
Not related to the previous question, but can you explain how elliptic curves had played a role in this?
Yes, thank you for the question. So,
Thanks for asking a math question.
so if you look at this process, we started with some number g. So instead of number, I could start with something inside the elliptic curve g. And I could fix some number a in my mind from the elliptic curve a. And I could also use the number b from the elliptic curve. Then since elliptic curve has these operations of say multiplication, I can compute these inside the elliptic curve. Similarly, I'll have a key inside the elliptic curve. So you do all this operation in the new addition in the elliptic curve, and you get the secret key.
Could you show an example on an elliptic curve? In the sense that we have some lines and stuff. Are they symbolic of something?
No, the addition operations.
Yeah, could you just explain that? Maybe that's a
Right.
fun thing.
So if you look at the last figure here, so how do you add 2 points on this curve? So you have P here, you have Q here. So you draw a line from P to Q, it intersects somewhere to the curve, and you look at the mirror image. So this point R is actually P plus Q. So you have P plus Q plus, this is minus R then, minus R is 0. This is the addition on the curve.
So similarly from addition, you can also define multiplication, and whatever procedure we are talking about can be done on the curve itself. And as you can imagine, like it's some curve that you choose and do all sorts of things. So it is, as she promised, it is complicated.
Yes.
So as I understand that the whole encryption, the security is involved on that mathematical things, which is the multiplications of 2 prime numbers, and we will get another numbers, and that numbers will be act as a cipher the message.
Yes.
Right?
Yeah.
Okay, now if any persons can get that the number, they cannot refactor that the number, right?
Yes. Yes.
So they cannot get the message.
Yes.
But that you have shown that if that number, it will take some time, right?
Yes.
Then some, right? But right now, if you see that the quantum computing is getting traction,
Yes.
and we can,
Yes.
any persons can with a wrong mind, right? They can cipher
Yes.
that thing,
Yes.
and then the whole mathematical blocks will break.
Right. Yes, that is true. These methods.
So then
they can-
how that thing will work in the future? Because you can see that the quantum computing is like IBM, you have seen the quantum computer, right? So any person can break the things.
So I guess the easy answer is you have to come up with more and more complicated systems, even for beating the quantum computer. Yes,
See-
Chris, please go.
Oh, okay. So, to answer your question, so one of the reasons why people got very interested, at least public at large got very interested, or funding agencies got interested in quantum computing, is because of a particular algorithm which does exactly what you're saying, which we can actually find prime factors of large numbers. And the point is that, as you can see over here, you have just changed the number of digits from 200 to 300. That's just a small factor on top of there, right? 1.5 times. You see the number of years it has grown by 10 to the power 6. Just changing 1.5 in the number of digits, multiplying 1.5 number of digits, creates a change in time which is 10 to the power 6. This is an example of exponential growth in complexity. What shows the algorithm showed is that yes, if you give me a larger number, it will take more time, but not such horribly large times. It is still workable. In the sense, it is efficient in the sense that you can factorize it in polynomial time, what is called polynomial time, in the sense that it will not grow like the curves you saw for COVID, which were just going like that during the second wave or whatnot. So the point is, so what showed is that the way that we do encryption, which is based on prime numbers, is vulnerable to quantum computing. That's what we actually shown. But as she showed you, there are other ways of encrypting, right? Which quantum computing cannot take a crack at. So the answer over there is that yes, one very established way of doing cryptography is vulnerable to quantum computing. Does not mean other techniques of cryptography are vulnerable to quantum computing. So there are different ways that people are trying to do it. In fact, so she was talking about key exchange. There's also a quantum version of key exchange that labs in TF are actually doing experiments on. There's already somebody in the audience who also works on who works in a quantum computing lab. So if you're interested, they can talk to you now.
Thanks.
That's fine, but that's okay. And there are also other people in the computer science department in TFR who are actually looking at these problems as well. So the future will be bleak. One of the things that people said that yes, it is impossible to break, quantum computing can break, but there are many other things which can be mathematically proved to be robust. And that is the main point. But it requires you to get more and more complicated mathematics, the techniques. I don't know much myself, but that's the little bit I know.
We had a question among the student audience.
Please.
Yes, the answer is because, let me go to the slide. So if you observe here, so the question here was, if you know these three numbers, G power A, G power B, and G, can you find this? So if you look at the carefully, an easy way to look at find this number G power A B is you take the log, you'll find A, and then you can just do G power B power A to get G power AB, right? So if taking logs were easy enough, if it would take less time, then this will be really a bad system. But on elliptic curves, it is very hard. It's even harder than this to take logs, like find, yes, logs. Another question here.
What happens if we use a mix?
Sorry?
Like, for example, we can, let's say there's a code, like there's two sentences. First sentence, we can use the first word, we can use this Diffie-Hellman.
Right.
And then the second one, we can use Caesars. Third one like that, so it will be harder for them to decipher, right?
Yes, that can be done. You can combine more and more complicated methods together. But and decoding thing also should be easy for the person to do.
Okay. Sometimes we just like make like a list, like for example, A is G, X is C, S is L. Like, there's not much of a logic. Only we two know, like only the sender, the decoder, and the writer knows.
Right.
It's like that.
Sorry, I don't understand the question.
Like for example, let's say like random letters. For example, X is like this is G, like I have to make random letters. And we can't decipher it.
But you have to transfer the whole list to the person who's decoding it, right? And if it gets like somebody gets hold of the list in the middle, it will be a problem. They can also decode the messages. We have another question here.
This is slightly more mathematical question. What's the general equation for an elliptic curve? Like
Correct.
the one that was shown in the PPT.
Oh, yeah, it's, I think y cube is equal to ax square, sorry, y square equal to ax cube plus bx plus c, that's,
It's a
Yeah.
y square equal to something.
yeah.
Yeah, you should put it in the projective plane also and compact it.
Yeah, there's a lot of things here. This picture is not very honest, it's, like, it's. not
We have
honest.
a few minutes if you want to expand upon that.
Yeah, I mean,
It's okay to expand upon.
no, it's fine.
No, okay, fine. But then you can talk in private. Further questions, comments?
Okay, so if there are no further questions, I think we're done with the talk for math, and I hope everyone likes cryptography and learn a bit more about it. So we would break for a lunch break right now, but we have another talk, which is a scheme which is from the biology field, which talks about brain and building a brain. It is one of the developmental biology, so coming from developmental biologists. So people please stay tuned for, and come back over at 2:15 is what I urge. Thank you so much.
And otherwise, later on, we have a public lecture by the director of the institute about the radio astronomy program in India and how you can actually see stars as well. Thank you. Thanks for your interest. Have a good time exploring the